Welcome. This is section 3-4 in chapter 3, and we're going to be discussing measures of relative standing. So what we'll be doing is learning a couple of formulas. One is called a z-score formula, and a z-score formula allows us to compare different types of values from different data sets. And then box plots is another type of statistical graph, and we'll learn how to graph those. This is also something that you would need to know how to do for the next exam. There are several different types of standardized tests that students take when they're trying to get access into colleges. One of those is the SAT exam, and the other is the ACT test. And depending on which part of the country you live in, that determines which exam you would take. And those two tests are entirely different tests. And so if we wanted to know if a student, for instance, got a 30 on the ACT, that sounds like a really low score compared with the top score from the SAT, which I think the top score for that would be a 1600. How do we compare those scores since they're so different? And so what we do is we have a formula in statistics that allows us to take these scores from very different tests that have different means and different values in them, and we can compare those scores and determine which one is the better score. And so to do this, we have a conversion formula called the z-score formula. And so on the z-score formula, the formula is z equals x minus x bar divided by s, or z equals x minus mu divided by standard deviation, sigma. So I just wanted to point out that both of these z-score formulas are really the same thing. It's just x bar and mu are both the mean. And so x bar is the mean of a sample and mu is the mean of the whole population. And then s and sigma are both representative of the standard deviations. So really the z-score formula is x, your score x, minus the mean divided by the standard deviation. So z-scores are used to compare values that could come from very different populations that have different means and different standard deviations. And z-scores actually let us plot values on an axis like a number line, and positive z-scores are above the mean or above 0, and negative z-scores are below the mean. And most values, 95% of them, fit between the z values of -2 and +2, and that would represent traveling within 2 standard deviations of the mean. So a z-score between -2 and 2 means the value is in the middle 95% of all data values. A very interesting question in statistics is a value going to be unusual? And by definition, a value is unusual if it is smaller than -2 or larger than +2. And that's because this value falls in the lowest 2.5% or the highest 2.5% of all values. And that just follows from the empirical rule. Now in this example, we're going to look at Stanford-Binet IQ scores, which is the standard IQ test. And the standard IQ test has a mean of 100 and a standard deviation of 15. And Albert Einstein had an IQ of 160, and he was reportedly a genius. And so what is the difference between Einstein's IQ and the mean? So in math, the difference means subtract them. So we're going to take his IQ of 160 and subtract the mean IQ of 100, and we get 60 points different. How many standard deviations is that? And so we take 60 and we divide by the standard deviation 15 to figure out how many standard deviations go into that, and we get 4. Now let's also use the z-score formula that we just learned to convert Einstein's IQ score to a z-score. And so remember that the z-score formula is x minus x bar divided by s, or 160 minus 100, the mean, divided by 15. So you end up with, again, 60 divided by 15, which equals 4. So if we consider unusual IQ scores to be those that are outside of -2 or +2, is his score usual or unusual? And since his was 4, a z-score of 4, then that's very unusual. So that's another way to prove statistically that his IQ was way, way above average. Now you'll see that at the top of this page there is a link that gives you a video tutorial which you can watch multiple times. So if you'd like to click that link after you watch this PowerPoint, that would be a good idea. Let's say that 3 students take equivalent stress test. And so they each have their own value, their score that they received, and we want to know who had the highest relative score. So one student received a score of 144 on a test with a mean of 128 and a standard deviation of 34. And so what we want to do first when we're asked to determine who has the highest relative score is we want to do the z-score conversion. So this student would be 144, his score, minus the mean, 128. Notice that's in parentheses, so if you're using your calculator to type this in one step, you do need to put that in parentheses. And then we divide that by the standard deviation, which is 34. We get that this student had a z-score of 0.47. The second student received a score of 90 on a test with a mean of 86 and a standard deviation of 18. So let's convert that student to a z-score. So z is x minus x bar divided by s. So 90 minus the mean, 86, divided by the standard deviation, 18, gives us 0.22. And the third student had a score of 18 on a test with a mean of 15 and a standard deviation of 5. So you can see that these 3 students had very vastly different numbers for their scores, but we are yet able to compare them when we convert them. So let's convert this final student's score to a z-score formula. So we do z is x minus x bar divided by s, or 18 minus the mean 15 divided by 5, and we get 0.6. So, who had the highest relative score? Well, if you compare the 3 numbers of 0.47, 0.22, and 0.6, which one is further from the mean or the highest above 0? And we would answer this question that the student in part C actually had the highest score. So 0.6 is the highest value, that's the highest relative z-score. Outliers in statistics are values that are very far away from the rest of the data points. Outliers greatly affect the mean and the standard deviation. And they can also completely obscure important data on a histogram. Sometimes outliers are mistakes that the researcher made. And also, if we know that we have a correct outlier, then you have to determine which measure of center would be best to calculate. So it's good to calculate the center with and without the outlier, and then also create graphs with and without it, since the outlier is going to really influence and affect the way the shape of the graph is. And so you can see graphically here there's 2 different pictures. There's a bar graph and then a scatter plot, and you can see that how the outlier compares to the rest of the data. One thing that you'll have to know for the first exam and for the final is how to create a 5-number summary. A 5-number summary is another way to look at the spread of our data, and it also helps us create a specific type of a graph called a box plot. In a 5-number summary, we obviously are trying to locate 5 important numbers. The 5 numbers that we need to find are 1, the minimum value, the lowest number in our data set. And then After that, we have 3 different quartile values. Now, quartiles are medians. So what we want to do is calculate the median of the whole data set, and then we divide the numbers around that median. So we have the lower set of. Here's data that shows tree heights, and what we want to do is use this data to create a 5-number summary. So what we need to do is first make sure that your numbers are written in order from least to great. And so what I've done is rewritten all the values in order from low to high. The second step is to find the median. So if we count the numbers that we see in our list, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, and 20 numbers. So half of 20 is 10, and so the middle number is going to be between the 10th and the 11th numbers. So what I do next is I count to the 10th number, and I land on 3.9. I draw a line after 3.9, and that's going to be where the median is. And so how do I find the median? Well, when it's in the middle like this, between 2 numbers, we're going to add up the 2 numbers and divide by 2. So I take 3.9 plus 4.0, and that's going to equal 7.9. Divide that by 2, and you get 3.95. Okay, so now notice that we have the lower set of numbers, which comes to the left of that line that I drew. So on the lower set of numbers, there's 10 numbers. So half of 10 is 5. The 5th number is 3.1. So between 3.1 and 3.4, that's going to be the middle, because that balances the numbers again when I draw that line. And so what I want to do is add 3.1 plus 3.4 and divide by 2. So 3.1 plus 3.4 is 6.5. Divide that by 2 and you get 3.25, and that's the quartile 1 number. That's the median of the lower set of numbers. To find quartile 3, we need to find the median of the upper set of numbers. So the line that I drew in the exact middle, now focus on the right-hand side of that. And so we're looking at the values that start at 4.0 and go all the way to 13.9. Again, this is 10 values. So half of 10 is 5. So I'm going to count to the 5th number, and I land on 5.1. And so between the 5th and the 6th numbers is the median. So I add 5.1 and 5.2 and divide by 2. So 5.1 plus 5.2 is 10.3. Divide it by 2, and you get 5.15, and that's the 3rd quartile. So what you can see here is what we're focusing on is getting the numbers in order, and then what we're doing is finding the middle, the middle, the middle. 3 middles. There's 2 more numbers that we need to find for the 5-number summary, and that's easy. The minimum, 1.8, and the maximum, 13.9. And that completes the 5-number summary for the data of tree heights. Now, what happens if we remove one of the numbers from the original list? So let's remove the number 13.9, and here's the list that we now have. So if we remove that one number, I now have 19 numbers that are in this data set. So let's go ahead and figure out what's half of 19. So 19 divided by 2 is 9.5. So what I'm going to do is count to the 10th number, and that number should be exactly in the middle, so let's circle it. So the 10th number is 3.9. So if I circle that number, that leaves me with 1, 2, 3, 4, 5, 6, 7, 8, 9 numbers to the left of it, and it balances with 9 numbers to the right of it. So 3.9 is the exact median, and that's quartile 2. Now the way that we divide the numbers by the lower half and the upper half is the lower half is going to start at 1.8, and it's going to end at 3.8. So you take the median out of it. So let's find the middle number for the lower set of numbers. So I count over to 3.1. That's the 5th number, and that's exactly in the middle because that balances it with 4 numbers to the left and 4 numbers to the right. So quartile 1 is 3.1. Now let's find the median of the upper set of numbers that starts at 4.0 and ends at 8.3. So the fifth number is 5.1. We circle that, and that's quartile 3, and then just check to see that it balances. You got 4 numbers to the left of 5.1, and we have 4 numbers to the right of 5.1. Then we just have to find the minimum and the maximum, so we circle those, and there's our 5-number summary. Box plots are special graphs that are made from 5-number summaries. To construct a box plot, we find the 5-number summary that we just did 2 examples for. We're going to draw and label a horizontal x-axis. And what we're going to then do is create an appropriate scale. So maybe we go up by 1s or 5s or 10s to create an appropriate scale. And then we're going to connect the 3 middle lines and form a box that that goes around the 3 quartile numbers. And then we draw a line out from the edges of the box and connect to the maximum number and the minimum number, and those are called the whiskers of the box. Now let's practice making a box plot of the data. So here's the data that we've already used, and we found the 5-number summary for the data. And so what we're going to do is we draw a line and we create an appropriate scale, and you can see that this right here is a nice and pretty box plot that I did on Excel, but what I would recommend that you do is watch the video tutorial listed at the top of this page so that you can see really good step-by-step instructions on how I create a box plot.